can start.
All
So
right.
I'm going to introduce you. So Dr. Gaël Varoquaux is a research director working on data science at Inria, where he leads the SODA team. He is also co-founder and scientific advisor of Probabl. Varoquaux's research covers fundamentals of AI, causal inference, NLP, statistical learning, as well as applications to health, with the current focus on public health and epidemiology. He also creates technology, and he co-founded scikit-learn, one of the reference machine learning toolboxes. And he helped build various central tools for data analysis in Python. Previously, he worked at UC Berkeley, McGill, and University of Florence, and he did a PhD in quantum physics supervised by Alain Aspect, and he is a graduate from ENS Paris. So without further ado, I'm gonna let Gaël take the floor.
Thank you very much, Afaf. So I'm gonna share my screen and get started. So hopefully this should work. Yep. All right. So today I'd like to talk about tabular learning, and I'll span from data preparation to foundation models, which are a great promise. And an important point to start is that tabular learning is absolutely everywhere. Think about optimizing an industrial process. Think about detecting credit card fraud. Think about evaluating major health risks, the kind of stuff I work on, predicting airplane delays, detecting cyber attacks. Those are all real world use cases. So the point being that machine learning from tables has a huge impact on our lives. It's everywhere. Oops. What am I doing? Yeah. And so AI in the last decade has had amazing breakthroughs on images, on sounds, and text. And yet, as we've seen, maybe the most precious data is in tables. And the thing is that learning on tables isn't actually as easy as it seems. And we'll cover a bit the challenges. So just to set the picture, what I'm talking about is a table a bit like this. And what you can see is that it has, it has numbers, but it also may have categorical data. Here we have the sex, male, female. And the point being that the columns are all of different nature, and this will pose, statistical challenges. Typically, they have different distributions. And so we address, this heterogeneity via data preparation. So we might want to Gaussianize the different columns, standardize them, do outlier removal. And this is basically textbook statistics, because good preparation will facilitate the statistical modeling of the data. But it's very tedious. There's this old joke that in data science, 80% of the time is spent preparing the data, and 20% of the time is spent complaining about the need to prepare the data. So of course, the dream is, can more model tools such as deep learning facilitate this work? Because what we're really doing is we're basically transforming data. So can we learn it? And I'll first, start by showing you that it's not that simple, and that deep learning challenges on this. And that's a benchmark that we ran a few years ago, a fairly intense benchmark on many tabular data sets. And what we really showed is that tree-based models, such as, gradient boosted trees, just really tend to outperform deep learning approaches, even those that have been tailored specifically to tabular data sets. And so what you can see here is, we're looking at trade-offs in terms of compute time, well, prediction performance versus compute time. And what you can see is that tree-based models are both, better predictors and also cheaper. They use less compute resources. And I'm very happy to see here that, a very good trade-off is given by scikit-learn's gradient boosting, which is, tends to be both faster and better predictive. So what are tree-based models? Well, the way tree-based models really work is that they do feature by feature decisions. They take a sequence of simple decisions. So is the third feature lower than 0.8? Then I will predict that y is 37. And you can change these. And this comes with, one benefit is that it can naturally handle categories, because by handling categories, rather than a greater or smaller, you just test for equality, because with categories, you have a finite set of equality. Oops, sorry. So as I was saying, tree-based models can actually handle categories. They can also naturally handle missing values. There are often missing values in tabular data, and handling the missing values in the trees by typically special casing the decisions is much easier than imputation. And we've shown over and over that having approaches that adapt to missing value tends to predict better than working on imputation. And tree-based methods are really good for this. But there's something more fundamental, is that if we look at the data distribution in tabular data, and that's one example of tabular data, if you look at the different distributions of the features, they all have different distributions. And they tend to be very non-Gaussian. You can see that those distributions are, in the example I have here, most of them are positive only. They're very non-Gaussian. And the point being is that trees do not mind this at all. Trees are only sensitive to the order of the data points. So they work perfectly with this. And the fundamental challenge that we have here is that the Euclidean distance, the Euclidean geometry, doesn't really make sense in this data distribution. So the data distribution is neither smooth nor vectorial in a Euclidean sense. And this to me is really a fundamental challenge to the kind of tools that we use in deep learning or elsewhere that are based basically on gradient descent in vector spaces. So there's a tension between the kind of tools that we use and the properties of the data. So quickly what we learn is that the most precious data is in tables, deep learning struggles, and scikit-learn is still the most popular package. And it shows in the surveys. If you look, this is a survey on Kaggle, and if you look at the most popular packages, scikit-learn is the one that keeps coming on top. So I could end my talk here. But maybe I'm just an old fart out of touch, and I co-founded scikit-learn 15 years ago, and I'm still trying to be cool, bring it all back to scikit-learn. And yet, the numbers don't lie. If you look at the numbers of monthly downloads, scikit-learn is downloaded much more than PyTorch, for instance. You can check it online. You can find it on pypystats.org. Oh, wait. Pandas is actually downloaded much, much more than both of these. So what's Pandas? It's just a data frame library. It's not even a machine learning library. Well, what this tells us is that data preparation, once again and always, is the most important problem. And it's more important than scikit-learn or PyTorch. All right, so we need to dig a bit more there. And the point being is that data preparation is much more than numbers. So this is another example of a table. And what you can see here is that you have open-ended strings. You might need to normalize the information. You can see that I have social worker 4, social worker 3. We might want to separate the title from the seniority. We might want to bring in information from external tables, the employer or names that I could recognize, and I could bring in the information. And so we need more data preparation to deal with, typically to deal with strings. And this is a new challenge, but this can be a new opportunity because deep learning is very good at dealing with text. So maybe deep learning can come back. And here I want to talk a bit about the progress we've been doing on table foundation models. And if we take a step back, the successes of neural network in vision and text were either based on very large data sets or on pre-trained models. And so, can we replicate those ideas? Can we build pre-trained models? And here I want to do a segue in thinking about how we can enrich a table. And I'm going to take an example, but the point being is that we're going to be enriching the table via the strings that it has. And suppose I'm interested in the real estate market. Suppose I'm interested in predicting the price of a property, and I have a table, with different characteristics of the property, and one of the characteristics is the city. And we know that property prices will vary vastly from city to city. So we know that if we want to understand a real estate market, we're going to have to bring in extra information on the locality. And so we're going to do this by, recognizing the entities in the strings and then bringing in external tables to merge in the information. And so, this typically is done via database operations such as joins. And if the data source is a bit complicated, well, then it gets indeed complicated because, oops, I clicked on the wrong button. My apologies. No, am I still sharing? Yes, I'm still sharing. Okay. Sorry. Yes. So if the data source is a bit complicated, it gets really challenging because we need to merge the information across multiple tables, sometimes with multiple hops in the merge, sometimes by doing some aggregation. So we need to represent this data and summarize this data in a way that enables, the feature enrichment. And this is challenging because we have a variety of available features. We have a variety of the granularity of information, and the richer, the data that we try to bring in, the worse it gets. And so what we did a few years ago is that we looked at whether we could, embed a very complex source of data into vectorial embeddings. And here the idea is, can we distill the information that's in a very complex source of data into a vectorial embedding? And so here, here's an example of an embedding that we did that embeds all the information of Wikipedia in a vector space. And so we called this KEN, knowledge embedding with numbers. And let me walk you through a bit how it works. So the first idea is that we represent the data, the relational data, as graphs. So it's a well-known trick in knowledge bases. So we might have a triplet representation where each piece of information is represented as head relation tail. So for instance, I have a county, a locality. It's called the Harris County. And the relation that I'm looking at is the county population. So that's the relation, and the tail is 47 million. And so this gives us a graph that represents the information. And then we're going to adapt knowledge graph embedding approaches. And so what this knowledge graph embedding approaches is that they embed all the nodes of the graph in all the relations in a vector space that summarizes well the upstream information. And once we have this embedding, then we have vectors that are associated to the named entities, and we can bring them in a downstream task. So first, what's the equivalence between tables and graphs? So as I mentioned, a knowledge graph is a list of triples, head relation tails. So for instance, Paris is the capital of France. And it's important to see that the two representations of the data, tables or graphs, are almost equivalent. So if I take a table, here a table with city, population, and state, I can define a head column. And then every pair of head column to other column is going to define a relation. So city has population, city in state. And once I have this, then I can build my graph. San Francisco has population 0.87 million, is in state California. Okay, so I'm just, building the graphs. So there's really an equivalence. And likewise, the graph, which is, I forgot to stress, it's a multi-relational graph. So each edge has a relation associated to it, and there are different relations to their different edge types. And so I can take a given edge type and I can build a table, which is a table with only 2 columns, which is a table corresponding to this relation. So I can really go from the table representation to the graph representation equivalently. So once we've done that, we can look at embedding the information on this graph. And here, we can think about, for instance, the successes of natural language processing, which are contextual embeddings. So words in natural language processing are often embedded by looking at the co-occurrences. So 2 entities have embeddings if they co-occur. But with the kind of data we have, we can go one step further. We can look at relational embeddings. Here, we want 2 entities to be close if they have the same relationships to other entities. And so what's interesting here is that when I do these kind of relational embeddings, and then I can separate the information because I have different type of relations. So for instance, if I look at companies, a company may have been founded in a place. For instance, Facebook was founded in Massachusetts, but a company may be headquartered in a different place. Facebook is now headquartered in California. And so with the kind of embeddings that we're looking at, we're going to embed the entities, but we're also going to embed the relations. And so what you can see here in the embedding is that the relation headquartered is in a different direction than the relation founded in. And so with those 2 relations in a different direction, then we can represent the information, the different relational information, in a knowledge base that can be then queried along those directions. Okay, so how does it work? Well, I'm going to start with the seminal example of the historical method, TransC, which started by representing the relations as a translation. And so, Paris, capital of France, Paris is connected to France with the relation capital. And so then this gives us a scoring function. The head plus the relation should be close to the tail. And then, we're going to optimize the scoring function, and we're going to use basically a stochastic gradient descent with negative sampling to optimize this relation. So this is how TransC works. So we've actually, to build Ken, we've actually used another method or adapted another method, which is called Muri. And the benefit that it has is that it's good, for instance, for one-to-many relations. And let me come back to TransC. When you have one-to-many relations, so for instance, I was born in Paris, but many people were born in Paris. And so trying to optimize this kind of bijective link between people born in Paris is going to, try to push everybody who was born in Paris in the same neighborhood. So that doesn't really work well. So ideally, you want a relation that is non-bijective. And so one way of doing this is the Muri scoring function. And what it does is that it has a translation vector, R, but it adds an element-wise transformation of the head, which can create a contraction or a dilation. And so it helps, giving more wiggle room in the neighborhoods. And so it enables relational geometry like the one I was mentioning earlier, where what we're having here is a projection geometry. And in such a geometry, different directions will encode different information. So it's a really great way of representing this really complex set of information that's spread across multiple tables in a vector space. And so this is what we did with a few other tricks to get basically entity embeddings that really capture well, this background information. And so the nice thing is that we can take a really complex relational source, for instance, Yago or DBpedia or very complex sources with many, many tables, and represent it in a vector space. So for instance, you can download the 6 million common entities on the website of my group, and you can see here that we have cities, people, companies. All right, this was a bit of a segue because this was an important conceptual step for what we now have, which is a foundation model, a deep learning model that we call CARTE, stands for Context-Aware Representation of Table Entries, that performs much better than tree-based models on many applications. And the breakthrough was that we were able to enable pre-training, but this pre-training is actually useful because it brings knowledge, it brings background knowledge, which is what I was just presenting with Ken. So how are we going to, pre-train for data tables? If I give you just a bunch of numbers, what can I say about this table? Not much. But if I give you column names, a table title, entities that I can recognize in some columns, then I can bring a lot of prior information. And so the important point for me, for the kind of foundation models that we're trying to build, is that the column names and the string entries are important to contextualize, to understand the numbers. Still, how do we pre-train? There are well-known challenges in data integration. Basically, putting tables together is hard. They speak about different things. At the cell level, you're going to have different representation of the same entity, for instance, Londres and London. And so you need to do what's known as entity alignment. So we tackle this using pre-trained string or language models that create vectorial embeddings. At the column level, well, we have a challenge is that we're going to have different schemas. So, different tables have different columns that talk about different things. So we're going to tackle this by modeling the local relational structure. So specifically, when we're given a table, we represent it as a graph, as a multi-relational graph, just as in the knowledge-based literature. So each column then becomes a type of edge, and each value becomes a node. And then the cell values and the column titles are related to string embeddings that can be either on the nodes or on the edges. Once we have this, we can learn a specific kind of graph neural network that's based on the attention mechanism. So it's a form of transformer architecture. And because the benefit being that this representation allows us to represent any kind of table, any kind of relational information, actually. And so we pre-train, across very large data sources using contrastive learning. So basically contrastive one table row that actually exists, one graph that actually exists with one graph that doesn't exist. And this forces the system to capture, the kind of plausible tables. And on top of this, to have this work, we contributed a new attention mechanism that's related to the kind of relational information that I was mentioning just before. So the attention mechanism looks a bit like the mirror E scoring function that we had before. And so we pre-train this on very large knowledge bases. And at the end of the day, we get data processing that recognizes the data semantics. So you give me a table, implicitly it's able to relate this table to some information that it has captured during pre-training. So we call this this project CARTE, and you can download it on PyPy. And so the benchmarks, CARTE predicts best. And it comes with a marked benefit. You can see that it ranked over 42 dataset. It actually works much better than the challenger. So this is it. We have CARTE. It's a great deep learning model. It's a tabular foundation model. It's powerful. You can try it out. You can use it. It might be difficult to install. You might need a recent version of PyTorch. And it's resource hungry. It's going to use, lots of GPU or CPU. And that's problem because resource usage matters. Resource usage is a drain, even on the best founded startups. And that's just for the, rich countries. Don't want even to mention the fact that it's only a tiny fraction of the world. And so it's a very worrying trend, at least the trend that worries me in AI, is that we're basically using more and more compute power. The training of very large models has overtook the largest computers and has gone, much further. And this is a log scale, so this is a super exponential growth. And this is not related to Moore's law. Computing is becoming cheaper, but as computing is becoming cheaper, there's an increased demand that goes faster than the efficiency gains. And what you can see is that the cost of training just goes up and up and up, despite the fact that computing is cheaper. And we're getting numbers that are just crazy. I hear numbers around $100 million to train a large language model. Now, we might think it's okay because those models, they're trained once and then, they're used many times. But the problem is true also for inference, for using those models. What we can see is that at inference also, the cost of inference is going faster than the improvement in compute power. So there's a big question, of whether, the costs are going to add up, how sustainable this is going to be. Is this going to be inclusive or is this going to be for the rich? And here I want to stress that, this kind of race to scale benefits some actors. If we need, a huge amount of individual data, well, the social networks are going to have this amount of individual data. If we need very large compute, well, the hardware providers, whether they're the actual manufacturers or the cloud providers, are going to benefit most. So the economics of these developments is to keep in mind. And one danger is that these developments end up basically all being bought by the current tech leaders that actually have the capital necessary. So let's look again at those benchmarks. I told you CARTE is amazing, but maybe we can look at the others. There are some strong baselines. What we can see here is that some simple models can work well. Logistic regression is, not as good as CARTE, but it appears in some of the top performers. And what we can see here is that preprocessing matters a lot. So let me take a few minutes to talk about some old techniques which we're still working on. I said trees were amazing, but still trees will still need preprocessing. They will need to transform the strings. They will need to transform the dates. And so we have a new library that's called Scrub that really tries to make it as easy as possible to do this pre-processing and this feature engineering for tables. And so if you know scikit-learn, and Scrub has similar kind of feeling. For instance, there is the table vectorizer. So the table vectorizer, you can instantiate it, call it tabvec, for instance. And then you can fit and transform data frames. And when you fit and transform data frames, it does the data preparation for you. It will apply different heuristics for different columns. It will transform the dates and time columns using the date time encoder. It will transform the simple categories or the simple strings with one hot encoding. Strings that are more complicated, it's going to use more sophisticated method, like for instance, the gap encoder. And let me show you a bit what it does for you here. So the problems with those strings is that, they're basically open-ended categories and they break categorical encoding. So the kind of stuff that we do in Scrub is that we do substring modeling. So if you look at, those strings, you can find that they're kind of repeated words, repeated patterns in them. And so we're going to model them. And so we can model them using a latent factor model that's basically going to find, what's repeated in them and is going to encode those strings on basically a topic matrix, but it looks like a soft one-hot encoding matrix. So it has found latent categories, legislative, operator, specialist, and it's encoding the data as such. And this is a typical example of what we're trying to do in Scrub, less manual wrangling and more machine learning, and doing this in a way that's lightweight and interpretable. So, if we put things together, we have data tables and they're complicated, they're messy. And in Scrub, we have a tool that's called the tabular learner. You call tabular learner and you give it an existing model, or you tell it if it's a regression or a classification task, and it adapts the preprocessing to the model. And the way that by default it works is by using the table vectorizers with well-chosen defaults and the his gradient boosting model from scikit-learn. So it's lightweight and it's fast. And if we go back at those benchmarks again, what do we see? We see things like LLM and trees work really well. Cat boost actually works really well. But we also see that Scrub table vectorizer combined with simple models like logistic regression works really, really well. So, you can choose your poison. You can use CARTE. You can use deep learning. It's powerful. It's going to be more difficult to install and resource hungry. Or you can use Scrub. And in Scrub, we're interested in exploring the trade-offs to have it, easy to install and easy to adopt. And I don't have a conclusion today. I don't know which is going to be the most useful model. And they're probably both going to be useful depending on the application. So Scrub, does much more than I mentioned. There's now optional use of LLMs. You can use the text encoder, giving it a pre-trained model from Hugging Face, just the string from Hugging Face Hub. And then it will basically embed the columns using this model, and you can use it in a scikit-learn pipeline. So, with all this, I'd like to say, predicting from a messy table is pretty much solved. Scrub is about much more, and I will not be able to cover all of it. But let me give you an example. Scrub will help you for data exploration. There is a tool that we call the table report, and the table report gives you an interactive view of the table on which you can click to have the column distributions. It's very useful with, all those very different column distributions. You can look at the column statistics and you can see, for instance, that we have, missing values in the gender column. And the table report will give you information, for instance, saying, that we have two columns here, department and department name, that are very associated. And, it's telling us that there is a crime of E, so a link between these two, that's one. So they're very associated. And if we go back to these two columns, department and department name, what we can actually see is that there's a one-to-one mapping between those two. So that's one thing that the table report does for you. So I'm going to skip a bit the things that we're working on right now. I just want to say we're working on a super exciting thing that will allow you to do preprocessing, very complex preprocessing, with a simple syntax and giving pipelines, readily usable pipelines. All of this is open source, and you can work with this. It's still, you know, ongoing work. And in the interest of time, I think I need to finish. And I just want to wrap up by saying tabular learning is very important. It's less visible these days in the media because it's harder to understand this than to understand ChatGPT, but it's everywhere and it's having an impact on our lives. And there, data preparation is key. And I've shown, you know, Scrub, which implements lightweight tabular learning patterns. I'm very excited about it. I hope it will be very useful. I've also talked about tabular foundation models. What I've shown is how they can bring background knowledge, and I think they will keep improving more and more. Thank you very much.
Thank you very much, Dr. Varoquaux, for this amazing webinar. I will definitely try Scrub because I work with tabular data. Also, decision trees are my favorite kind of model because they're very interpretable. You can actually stop sharing your screen. This is more of a Q&A discussion. So I will start like by a very simple question. Does CARTE allow like this interpretability like to still be there from the models? Like, do we still have that part of simplest? Because I know it's like adding a layer of complexity, but it's not too black box in a sense. That does it still allow that?
No, CARTE is very black box. Interpretability is a difficult concept. I think well, first we need to, you know, define why we want interpretability. We want interpretability for different reasons. We want interpretability to debug, and by debugging, I mean debugging the data. Often we have to debug the data. We want interpretability also because we want to understand the range of validity of the model. So typically, you know, we find associations in the model that make no sense or that we know won't carry over. And so typically we might want interpretability for this. And for the second one, I typically like to think more about causal validity, about distribution shift. And I think that's really important. You know, someone who cares a lot about health applications, for instance, I don't think we can do them without this kind of thinking. For debugging the data or the model, I think we need to reinvent our interpretability tools and their ways. And so typically, I forgot how they're called, but there is a way of looking at taking the prediction of the model and taking one feature and looking at how the prediction of the model evolves given this feature. It's in scikit-learn. I forgot how it's called, but it's black box interpretability. Now there are arguments for white box interpretability, and the argument, so basically using models that are simpler to interpret. And the arguments are that it's easier not to miss any problem in a model that is simple to interpret. But you know, as I mentioned, I don't think there is a one size fits all, and I think linear models will still be around in 100 years.
I like that you mentioned distribution shifts because I was thinking, what would this kind of foundation model, where would it be more useful? You also mentioned the health sector. So I imagine this could be helpful to kind of learn more about diseases, trained like on different hospitals. But but we have some significant shifts. Like how far of a shift can this handle? Like, would they be fine-tuned? Because I imagine that based on the demographics, the features vary a lot from geographical region.
Yeah, so currently in the work I've presented, CARTE is fine-tuned. And this is really how we see it. We have later developments where we can use a model similar to CARTE without fine-tuning, which is the benefit of being much less costly. But where would table foundation models be most useful? I mean, where I'm excited about them is where the data is very complex. So if you work on an electronic health record and a hospital database, the amount of things that you need to know is pretty crazy. You need to know 50,000 codes of diseases, 50,000 codes of medication. You need to know jargon beyond these codes. You need to know, population. You might the demographics of people varies, where they come from. So there's this kind of plus you need to know things that are related to the reimbursements, to the function of the hospital, and it takes a lot of time to acquire this knowledge. And here I'm really excited that a table foundation model could help.
And what other applications do you see benefiting from this? I can see banks maybe.
Yeah, so typically the financial sector is quite interested in this. So typically, fraud detection in insurance or banks. Actually, insurance and banks are both interested and they're related topics. So yeah, banking and insurance. Those are domains that I also know. I'm convinced there will be applications elsewhere, but I know those domains less well.
Yeah, same. I just think of it with very basic knowledge of, like currencies are different, maybe like the average income is different. I always think in distribution shift, especially when someone mentions foundation models. I'm like, how are they going to be reused? So see that since you develop a lot of open source tools, how do you see the future of open source in AI in general, and especially for models and like also data? Yeah.
Well, models. We don't have many open source models. What we
Yeah.
mostly have are open weight models, and there's a
Yeah.
difference between the two.
Yeah.
But here, there's a challenge, and I think things are going to settle down. But as I mentioned, training a large language model costs something like $100 million. But the thing is, so it's mostly goes into compute, not only but mostly. And so the thing is that you run all this computation and you get your model out and you have your beautiful model, and then 1 year down the line, actually it's not 1 year down the line, it's 3 months down the line, somebody else trains a big model and outperforms your model by epsilon. Well, all this compute is basically thrown away. You've spent $100 million on GPUs. You haven't spent $100 million on software, on data, on something that will stay. And so, in terms of future, I wonder if that's the right way to do things, and I wonder if people will not just realize this. So right now, it's kind of a race, maybe a race to the bottom, but it's kind of a race. Yeah, it's an arms race. I can outperform you. I have more money and clever people. But we're not building. We're not accumulating reusable things. So I can foresee a future where we will try to accumulate reusable things, where we will try to accumulate curated data, where we will try to accumulate alignment material. Alignment is a very important aspect of large models, because this doesn't self-deprecate, whereas compute self-deprecates. So if we go back to your question, which was about open source, we need to think about those materials. We need to think about commons and data. We open source is completely the wrong term, but so we like to talk about commons, and one of the commons that we should all be proud of, the world should be proud of, is Wikipedia. It's an amazing thing. I spend my life on Wikipedia, and it's being done by many people everywhere in the world. And the question is, so the models we're talking about are models are basically embodying a huge amount of implicit knowledge. So the question is, how do we make commons there? And it's a race, it's a race between big capital and crowds. But I just don't think long-term big capital is sustainable because it's just such an inefficient use of money. We'll see.
I totally agree about the race for scaling things. It's also like goes even if you give the model as it is with trained weights and everything, only a few people can use it if they have the computer to use it. So it's a little bit uh lost.
The
Uh,
happy few.
yeah.
It's changing a bit because it's unsustainable. Those huge models are unsustainable. They cost so much to run that you need a large revenue stream, and there for most users there's no large revenue stream. And I'm talking about the inference cost. And so what we've
Yeah.
seen over the last month is that we've seen, smaller models that have been put out that are very capable and that you can more and more run on smaller hardware. We're starting to look at large language models that can be run on mobile phones.
Yeah.
And here, the driver is the dollar. It's important to keep this in mind.
It's always the case. Um, can you let us know more about Probabl and its relationship with scikit-learn?
Okay, so Probabl, the driver is the dollar. Probabl. Yeah, so scikit-learn, yeah, it's true. That's what it is. A
Yeah.
scikit-learn is above all an open source project that is driven by a community, but it still, requires people to be paid full time on it because it's not a hobby.
Mhm.
It's a mixture of people who do this on the side and people who do this professionally. And there are many people who do this on the side, by the way. But so we have this team, and for a long time, it was paid by grant money. Then it was paid by sponsorship by companies. And the thing is, it's doesn't allow us to be extremely ambitious. And we think we should be ambitious because if we're not covering the whole ecosystem. So how do you put a scikit-learn model in production? How do you connect it to a database? How do you do scheduled monitoring and re-updating of scikit-learn models? And so those are things that we didn't have money to work on. And so Probabl is a spin-off to complement the scikit-learn ecosystem. And it's not only about the scikit-learn ecosystem; it's about the broader ecosystem. You can see, for instance, I mentioned that Scrub can use language models, and when we use language models, of course, we didn't recode them ourselves. We connect to the broader ecosystem. And so Probabl has some, obvious services. We have some basically consulting team. We have a certification team. I don't know if people have seen, but we have a scikit-learn certification that you can take online and that is recognized uh, and basically certifies your skills in scikit-learn. But we're also working on a product that is a product for data science teams, that is a product for the enterprise that complements scikit-learn. And it's not out yet, so I can't share the details, but it's going to be out soon.
Awesome. So time is running up. I wish we could have talked more, but any last word for the Morocco AI community?
You don't get lured by the big models. Learn, statistical learning, and I stress statistical, and also will learn to code, to learn code, will learn to code things that are suited to your hardware rather than struggling to get, bigger hardware. Those are my words.
Thank you very much for the wise words in a world that is running around behind scale. It was a pleasure to have you, and I hope we can host you in future occasions. Thank you very much.
My pleasure. Afaf, thank you.